So, a very good morning and greetings of the day to all present here. So, my name is Navleen Kaur, and I'm going to cover a new topic under theory of computation. And the name of the topic is context free language, or you can say context free grammar. Okay, any language has no meaning until or unless there is a grammar defined for it. The grammar provides the rules and the language we develop based on those rules. For any language, if there is no grammar, it means that language has no meaning. Okay, so during this class, I will be using these two words alternatively, language and grammar. Okay, so they somewhat have the same meaning, and the topic is context free language, and previously we have done regular grammars. Okay, so now the question that comes to most of the students mind is that what is the difference between regular grammar or context free grammars. Okay, so during today's class I will make this difference clear, and for now, in a summarized way, I can say you that regular grammars are used to define a language that your finite automata machines can understand. Okay, I am repeating this thing again, that regular grammars actually provide the rules to create a language which is known as regular language. And who is going to use this language? I am not going to use, because human being never uses such languages. These languages are developed for the computing machines. Okay, so which machine is going to use your regular grammar or regular language? It is the finite automata machine. So your finite automata machine understands only the regular grammar, like in the form of whatever you were writing, the strings you were passing to it, the productions we did on that day. On the other side, have you noticed that most of the machines that we are working in real life, they have input, they have output, they have certain states through which they pass, right? Every machine has a way to get the input, and on the basis of that input it goes through certain states and it gives you the output also. It means that is a finite automata machine. But have you found a difference that the general machines don't only have input, output and states, they also have memory, they also have storage capacity. So if I talk about computer, so computer is a computing device, it is a machine. And do you think that to computer you give input, it goes through certain states and give you output, that's it? No, it is actually storing your information also, it has a storage also. But the finite automata that we did till now, we have not talked about the memory part over there. It means that finite automata machines are those machines which have no memory component. Okay, so for such machines we use regular grammars and regular language. But otherwise, most of the machines in real life that we are using, they have input output states and they have memory also. For such machines, if you want to develop a language, you want to create a grammar, the name of that grammar will be context free grammar, and the language will be context free language. It means this context free language we cannot use for finite automata machines. Okay, so for finite automata machines we have regular grammars. For the machines with memory also we use context free language. Okay, so if there are machines which has no memory, we call them finite automata. What will be the name of those machines which has memory? The name of such machines are push down automata. Okay, the name of such machines which has memory, which has input output and states, but also memory, the name of such machines are push down automata. And we will discuss this topic also in further classes because it is in unit 2 of your syllabus. Okay, and for these machines we have context free language, or you can say we have context free grammar. So if I have regular grammars with me that we did during our last class, they are for finite automata machines. You know, this is a machine. Okay, machine understands some language or some grammar is used to create that language. So regular grammars are used for finite automata machines. But now today we are doing a one new kind of grammar, that is context free grammar, short for CFG. So CFG we can use for actually, okay, we can use that for finite automata also, but the main point of CFG is that we use them for those machines which has memory also. Finite automata machines has no memory, so regular grammars were working fine with them. But as your push down automata known as PDA have a separate additional component which is known as memory. Okay, so these regular grammars can't work for your PDA, so this is cross. However, your CFG is at the higher level, it is superset. So CFG was developed to work on push down automata machines which has memory, but it can also be used for finite automata machines. So CFG was developed to work on push down automata machines, but as it is a superset, it is a more like good language, it has more advantages, so you can use it for finite automata also. On the other hand, this regular grammar, it was only used for finite automata machines, and you can't use it for PDA, push down automata machines. Okay, only for finite automata. But the CFG, you can use them for push down automata also, and you can use them for finite automata also. So any grammar that we define, if you remember the regular grammar, all the grammars, they have same components. Okay, so if you remember that we have defined regular grammars in the last class. So similarly, a context-free grammar. Context-free means it is free from any context. It is free from any context means that it can be used for anything. It is not sensitive. Sensitive means I will be used for this and not for this. Okay, it is free of any context. It means if the context is finite automata, it will work for it. If the context is push down automata, it will still work for it. That's why the name is context free. Okay, for which context you are using it, for finite automata or for PDA, it doesn't matter for it. Okay, because it is not sensitive about context, instead it is context free grammar. Okay, so it consists of it has finite set of grammar rules, and it is defined as a quadruple. It is used there are 4 tuples. Quad means there are 4 tuples that you use to define it, and obviously it is a grammar, so it has certain set of rules. Finite means you can count the rules, it's not infinite, it's finite set of grammar rules, and you can define it with the help of 4 tuples. These 4 tuples are the same that we used in regular grammar also. So if you remember n, it is a set of non-terminal symbols. You remember non-terminal symbols, all the capital ones, A, B, C, even S, right? The starting symbol. And T is a set of terminals. Okay, so what were the terminals? Terminals were the small ones, A, B, C, and mostly we have used 3, right? So can you see here that here this thing is mentioned that if you do the intersection of non-terminals with the terminals. What do you mean by intersection? Intersection means that if I want to find the common between the two, so suppose I have a grammar, and for that grammar I have non-terminals A, B, C, and S. Okay, and I have terminals A, B, and C. Okay, if I do the intersection of these two, non-terminals and terminals, intersection means it consider both the sets, and out of the both sets it will just write the common values when you do the intersection. But can you see there is no element common in these sets. So what will be the output? Output will be a null set, blank set. So what does it mean? It means that N and T, your non-terminals and terminals, should have no common element. N will be separate and T will be separate. Only then their intersection will be null. So this is a rule. Okay. After that, we have P. P means the set of rules, the set of productions. Okay. So your productions are defined with P, and they always start from a non-terminal, means a symbol which is in uppercase, like this, A, right? And production will go like this. Okay. And from this production, you can generate maybe a terminal, or you can also generate a non-terminal. So can you see that it always starts with the non-terminal, and what it generates a union of both. Means you can use a mixture of both non-terminals and terminals. So I have used a non-terminal also, I have used a terminal also. And star means you can use these non-terminals and terminals any number of times. Okay. And S is the start symbol. So every production starts with the an S. So for example, you are given a context-free grammar. Okay. From that, you can generate a tree. Okay. So now the topic is generation of a derivation tree. It means I am going to generate a tree. I'm going to drive a tree from the grammar. Okay. So what is it is called? Sometimes we call it a derivation tree, or sometimes we call it a parse tree. It's an ordered. It means it has an order. When you start from the root of the tree and you go all the way to the bottom of its branches, there is an order that it will follow. Okay. Now what's that order? I will tell you. So for now, you should only focus that it is an ordered rooted tree. Rooted means it has a root node at the beginning. Okay. And this rooted ordered tree graphically represents the information, semantic information. Semantic means all the grammatical information of a string, any string that you have derived from a context-free grammar. Okay, you know your grammar have strings. So here strings means, but I mean that they have productions. Okay, so strings means you have productions, and using those productions of the context-free grammar, you can derive a derivation tree or a parse tree. Okay, so how you represent your tree? There are three parts. First is the root vertex. So the start symbol, you remember in your production, there is one S, start symbol. So the root is always labeled by the start symbol. So it means the root is S, the start symbol. Next is vertex. You know that these are the vertexes. These edges are the vertices. Okay, so vertices are always labeled by non-terminal symbols. So non-terminal means like N, A, B, C, capital letters. So vertices are labeled by non-terminals. And leaves. Whenever I start a tree, so this is a vertex. So suppose I label it with A, and this is a leaf. So leaf will be your terminal symbol. What are the terminal symbols? Small a, b, and c, or even it can be epsilon. This symbol we have done already in regular grammars. Its name is epsilon. Okay, E-P-S-I-L-O-N. And you remember I have told you that this is known as null. Okay, so it means that maybe a terminal symbol is generated. For example, if I write A goes to A, it means this non-terminal goes to terminal A. Sometimes it is also written that B goes to epsilon. It means B goes to null symbol. Okay, so sometimes your leaves, they are labeled with non-terminals, or in worst scenario, they can be labeled with an epsilon also, which is a null symbol. So if you have a context-free grammar, so every grammar is made up of terminals, non-terminals, start symbol, and then there is a production. So what is a production? A production is a kind of string. So if I write A goes to BA, so it is a string. So using these productions, I can drive a tree. Okay, so your tree is having a root vertex. So from the grammar, the start symbol represents the root vertex. Okay, the vertices, other vertices, they are represented by the non-terminals, and the leaves, they are labeled by the terminal symbols or maybe with an epsilon, which is a null symbol. Okay, so here is an example. So suppose this is a very simplest example. Okay, so if your S means the start symbol, it goes to x1, x2, and so on xn. So can you see this x1, x2, and so on xn? These are in lowercase letters. They are small ABC letters. It means this S goes to x1, x2, so on up to xn represents what? It represents that your your start symbol is going to these small letters. So these small letters means ABC kind, small ABC kind. So small ABC letters are what? They are, sorry, terminals. For example, like this, S goes to A, B. It means your S is going to terminals. So here, terminals are always used to represent the leaves. Okay, so this tree becomes like this. So this is your root node, and as you see, there are not known terminals. There no information about the known terminals. So directly we have the start symbol, and these are the vertices. Vertices are not labeled because we have no non-terminals explained here. And the leaves, this is the leaf number 1, this is leaf number 2, this is leaf number 3. They are represented with the terminal symbols x1, x2, and any number of terminals that are present in your production. So for tree derivation, there are two approaches that you can use. Okay, so there are two different approaches to drive a derivation tree or a parse tree, or to draw a derivation tree. The very first one is top-down approach. Top down means you start from the top of the tree and you go all the way to the bottom of the tree. Okay, so in this approach, you start with the starting symbol S. It means you start from the root. Top means you start from the root. So when you are starting from the root, it means you are starting from the starting symbol S. Okay, starting from the starting symbol, you goes down to tree leaves. You goes down to the leaves. And how you are going down to the leaves? Using the productions that is given. For example, if it is written S goes to A, so what or B, so what you do? You will write S, A, B like this. Okay, this is one approach. And in the further example, I am going to use this approach to create a derivation tree. The second one is the reverse approach, which is known as the bottom-up approach. So in the bottom-up approach, right, you start from the bottom of the tree and you go all the way to the top. So if you start from the bottom, it means you first start from the tree leaves and proceeds upward to the starting symbol. It means the root S by using the productions. So there are two approaches, and I am going to explain the very first approach. So derivation or yield of a tree, it means if I am deriving a tree or I am creating a tree. So these two are synonyms. Okay, so the derivation or the yield of a parse tree is the final string obtained by concatenating the labels of the leaves of the tree from left to right, ignoring the nulls. For now, I am just avoiding this slide. Okay, first let me explain the example and then I will come back to it. Okay, so suppose this is an example. Look at the screen. So here we have a CFG, context free grammar. Okay, and it is made up of quadruples, means non-terminals, terminals, productions, and start symbols. Okay, so non-terminals, which non-terminals are available? There is only one non-terminal. Can you see? Only S is the non-terminal, single non-terminal we have. Otherwise, in most of the productions that we did, there were more than one non-terminals. You remember we have done productions like this where there were 3 non-terminals or 2 non-terminals, right? But we are provided with this context free grammar, right, which has only one starting symbol as the non-terminal. And if we talk about the terminal symbol, so we have, let's write here that we have only, let's don't consider it, we have the only one non-terminal, which is the starting symbol. And the terminal symbols we have are two, which are A, comma, B. Okay, so these two sets, the first two are done. After that, we have starting symbol. You know that starting symbol is already S, so starting symbol is S. Now we are provided with the productions also. This is a production. Okay, so what's the production given to us? A production is that S will goes to double S, or this S will go to ASB also, or this S will goes to epsilon also. It means that this S can go to SS also, that from S you can derive double S also, from S you can derive ASB. Okay, this pipeline operator means that from S you can derive this also, you can derive this also, or you can derive this also. Okay, so this single production represents what? It represents S can generate SS, S can generate ASB, or S can generate epsilon also. Now don't focus on this line, I will come to that line also. Okay, just see here. So derivation starts. Okay, so the very first production is that your S will goes to SS. Can you see this one? You always start from this one, that your S goes to SS. Very first, S goes to SS. So it is written here, S goes to SS. Okay, after you get S goes to SS, what is written next? Now from this SS, can you see that this very first S is replaced. This very first S is replaced, and in its place, what is written? In its place is what is written? This thing is written, that in place of S, you can also write ASB. You can see here, I am writing it. That very first is S goes to SS. Now in this SS, the very first S can be replaced with ASB. So can you see this ASB is coming here in place of this S. Okay, so in place of this S, what is written? ASB. And then this S is written normally. After that, this production is generated. Now how this production is generated? Now this S here, this S, it can be replaced with phi, epsilon, null. Okay, so A, this is replaced with null. When there is null, you don't need to write it. So I am just removing it. So B is generated, A, B, and I have S only. So can you see this is generated now? So this is the output of doing changes in one S. You know that it has two S and one S is changed. This S is changed. From here it reached here. From here it reached this here. Other S is intact. It is still the same. So we have productions. These are the productions. S goes to SS, or S goes to ASB, or S goes to epsilon. It means wherever S can come, I can replace it with SS. I can replace that S with ASB. I can replace that S with epsilon. So now I am starting. So I have to always start from the very first production. So I am writing S goes to SS. After that, this very first S, I am replacing it with the ASB, right? S goes to ASB, it means this S goes to ASB. This S is coming normally like this. After that, this S is replaced with an epsilon. It means in place of it, an epsilon is written, it means null is written. So null means it is just crossed, removed. It means we are left with A, B, and S. It means we have reached here. Okay, so if this is clear, let me take you to the half. We will do this also. Let me take you to the tree now. Can you see this is the tree? So here we have the S, the starting symbol. The root node is represented with the starting symbol. Okay, after that, this starting symbol is generating 2S, the 2 leaves. This is first leaf, this is the second leaf. Okay, now the very first leaf we changed. Can you see how we changed it? The very first leaf, this one, this S, it goes to ASB. So can you see this very first leaf goes to ASB? And after going to ASB, I'm talking about only this. This S goes to ASB. Can you see this S goes to ASB? This ASB. And after that, from here, this S goes to only what? It goes to only phi. This S goes to phi, and we are left with only AB. Okay, from here, right, this AB, this ABS that we got, this ABS that we got, this AB I'm writing normally, this AB. Now this S, this very first S is replaced with ASB. Can you see from AB, this S is now changing and it goes to ASB. So can you see this S is changing to ASB. Okay, now from ASB, after this ASB, what I am doing, I'm again changing it once more. So this ABASB I have got from here. Okay, now what I am writing next, I'm writing ABA as it is, and this S is again changed. And again it is changed to ASB, that is ASB, this S. And B is written as it is. So you got this one. It means this S is changing one more time. So I am only changing S. S is going to A, S, and B once more. Okay. After that, after you got this S is changed and it becomes epsilon. So what is the output? A, B, A, B, B. This is the output that you get when you just change the last one to epsilon. Okay. So what is the yield of this tree? The yield of this tree is this final string that you get, A, B, double A, double B. Can you see? The one derivation from the above CFG is this. There are multiple options. There are multiple derivations you can create. Okay. So this is the one derivation, A, B, double A, B, B. So when I was telling you what is the derivation? So the derivation of a tree is the final string obtained by concatenating the labels of the leaves of the tree from left to right. If you just concatenate the labels. So what are the labels? Labels become A, B, A, B, B. A, B, A, B, B. So these are the labels you concatenated, A, B, 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 and you got this string. Okay, even if you go from here and here, you will get this string. So this is known as the yield or string, derived string. And when you move from left to right, you always ignore the nulls. It means you never consider epsilon. However, if all the leaves are null, it means at the end all the leaves turned out to be null. So you can say that the derivation is also null. So like the regular grammar properties, if you remember that in the regular grammars, we did certain properties that regular grammars, they can undergo union. You can do union of two regular grammars, and the final grammar that you will get out of this is again a regular grammar, right? You can do the concatenation, you can do the intersect of regular grammar, you can do the difference of regular grammar, and complement was also there. So there were 5 properties of regular grammars. But if we talk about context-free language, these context-free languages have the following 3 properties. So they are closed under means they have the following 3 properties. First one is union, second one is concatenation, third one is clean star operation. Okay, so let's do these. Okay, so suppose very first property that I am going to explain is the union. Okay, so suppose there are two grammar. Obviously, if you are doing union, you need minimum two things. Okay, so in this case, you are doing the union of grammars or languages. So I am saying that let L1 is one language and L2 is the second context-free language. Okay, so if you do the union of L1 with L2, the final grammar that is generated is also context-free. Okay, so here it is written that suppose L1 is of the form a raised to power n, b raised to power n. Okay, so what do you mean by a raised to power n, b raised to power n? Till now we have not done grammars like this, a raised to power n, b raised. It means a is repeating 5 times, b is repeating 5 times. So if you want certain things to repeat 5 times, I am giving it a hint. Okay, repeat for 5 times. It means there should be a variable to store how many times a will repeat, how many times b will repeat. It means it needs storage. That's why I was telling you that context free languages work for those machines which require storage. Okay, so the language has the strings of this type where n is greater than 0. It means 1 2 3. This n is always greater than 0. It means it can be 1. So the corresponding grammar will be of the form, suppose that the starting symbol of L1 goes to this. This is a random example. And there is an L2, right? And their grammar is of the form that starting symbol of L2 is S2 and you represent it with this. When you do the union of L1 with L2, represented like this, L1 union L2, so what it will become? It become this ANBN union this CMDN. Okay, so you are doing the union of these two, and the final grammar will have the additional production. So these two productions will be there. This production will come from language 1, this production will come from language 2, but there will be an additional production, that a new starting symbol that will help you to reach S1 also and S2 also. Using that starting symbol, you can reach to the grammar of S1 also, you can reach to the grammar of S2 also. This is the union. Okay, and this grammar will also be the context-free language or context-free grammar. After that, we have the concatenation. Concatenation means you are doing the kind of product of these two. So if L1 and L2 are context-free languages, then L1, L2 are also context-free. So concatenation means you are doing L1, L2 and you are just doing the concatenation. So the final grammar will have additional production S that goes to S1 multiplied by S2. So these are just the properties mentioned. We are not going to do any example with respect to it. So we have to just define the properties. Okay. The third one is the clean star. Okay. So it is like the complement. You remember the complement of a set. So the complement operation we always perform on a single thing. Similarly, if you are doing the clean star of any language, so you need only one context-free language. So if L is a context-free language, then it's L's clean star. This star is represented as L clean star, and it is also a context-free. Okay. So if L is a language which is represented by this, so corresponding grammar, it has this. So the clean star of L1 will be ANBN's star. This is ANBN. So its clean star will be AN B raised to power n's star. Okay. And the final grammar will have one additional production. The final grammar has the additional production S1 that goes to S, and S means the previous grammar and the current grammar's production like this and epsilon. Okay, so it is different from this normal concatenation where two grammars productions were reached from S. But here, previous grammar's production and the new grammar start. S is the L, this S1 is the L star. Okay, so the new grammar's production you can use to reach to the previous grammar production and to the new grammar production, and you can use it to reach to epsilon also. Okay, so this is a theoretical concept and it has no example related to it, and I hope that it is clear. So we were working on the grammars. Okay, we have done regular grammars. Now I am telling you this context free grammar. I told you regular grammars work on those machines which have no memory, like finite automata machines. This context-free grammars, they work with the machines with the memory, known as push-down automata machines. Okay, so generally the question that comes to our mind is how many grammars are actually present? So there was this person, Chomsky, who gave the classification of grammars. Okay, he told us about the types of grammars available. So according to Noam Chomsky, there are how many types of grammars? 4 types of grammars. Okay, the very first type is known as type 0, then there is type 1, then there is type 2, and then there is type 3. So there are 4 types of grammars starting from 0, 1, 2, and 3. Okay, and the following table, this is the tabular representation. The following table shows how they are different from each other. Okay, so we always start, let's start from here. I'm not going to explain all of these because all of these are not in your syllabus. Okay, so the very first that we did in the last class, that is known as the type 3 grammar. Okay, it means that when a grammar was created very first time for a machine, for a finite automata machine, it was named type 3. Okay, and it is known as, what is the type of grammar? It is the regular grammar. And which language this grammar is accepting? The regular language. Okay, and what kind of automata? It means what kind of machines are using this grammar? Finite state automata. Okay, finite automata machines. So this was the thing that I was explaining in the beginning of the class, that your type 3 grammars, if someone will ask you question that what is the type of regular grammar, so you will say that these are the type 3 grammars. And what are some properties of this type 3 grammar? The properties are that they are regular grammar and they are used for creating regular languages, and these regular languages are accepted by finite automata machines. So these machines are having no memory, so regular languages can be used to implement it very easily. After that, there is this type 2, the one that we are doing now, the context-free grammar that we are doing right now is of what type? It is a type 2. After type 3, this type 2 was created. And the name of the grammar is context-free grammar. And the language that is accepting this grammar is context-free language. And which machine is used? Which machine is using this language? Push-down automata machine. And I told you that what is a PDA? PDA is that machines which are like your finite state automata machines, but the only difference is that your PDA has memory also. Okay, later on there are 2 more types, that is type 1. Okay, so context free means it can be used for both push down and finite automata. Then there came type 1. It is sensitive. It means it will not work for anything. And the language is known as context sensitive language, and the automata that uses it is the linear bounded automata. This is not a part of your syllabus. The last one is the type 0. It is unrestricted grammar. It is recursively enumerable language. We will discuss it when we will do the Turing machine. Okay, so Turing machine was the machine that is using the type 0 grammar. So till now, we focus mainly on type 2 and how it is different from type 3. And this Turing machine is also in your syllabus. And when we will do it, I will also explain the type 0 grammar too. Okay, so just if you go through over this type 3 grammar, so they generate regular languages. It means that using this, you can generate regular languages also. This is at the top. Type 3 is at the top. It means type 3 language can be used for anything, for Turing machine, for finite automata, for regular, for anything. Okay, and how they look like? They have a single non-terminal on the left side. Okay, so on the left side in the production, there is only one single non-terminal, and a right side consisting of a single terminal or single terminal followed by a single non-terminal. So it is sure that on the left side, we have only single non-terminal. It means capital letters. But on the right side, there can be a single terminal also, like this, sorry, this one, a single terminal only, or a single terminal followed by a non-terminal. Or there should be one addition that I want to do here, that there can be an epsilon also. It means there can be a null symbol also. There can be single terminal on the right side, or a single terminal followed by a non-terminal, or an epsilon also. Okay, so the productions, if you see, they are of the form x goes to a or x goes to ay. These are also the productions. So they are of the form that x goes to a or x goes to ay. Okay, where x, y, they are the non-terminals and a is the terminal. Now, can you see here the rule that s goes to epsilon? It means epsilon is allowed. It means you can write it here that any production rule s can goes to epsilon if s does not appear on the right side of any rule. Now, this is allowed only if your starting symbol is generating epsilon and your starting symbol is not appearing on the right side. Only then you can use it. I'm not. So type 2, they are known as the context free, and the productions are of the form like this. A goes to this xi, where A, this A, these are the non-terminals. Okay, I told you that on the left side you can have non-terminals, and xi, this xi means on the right hand side you can have terminals and non-terminals combination any number of times. Okay, so these languages generated by these grammars can be recognized by a non-deterministic push-down automata. It means when we will do push-down automata, then I will make it clear that it is also of two types: deterministic push-down automata and non-deterministic. So this is an example here, that here in this case also, on the left hand side also you have only one non-terminal, and on the right hand side you can use a combination like x, a, x. And how it is different from your regular grammar? In the case of regular grammars, on the left hand side there is non-terminal, so they are same in that context, both are same. But in case of regular grammar, on the right hand side there can be a single terminal. Okay, so they are also same in that context. Okay, and there is one single terminal followed by a single non-terminal. Can you see? There can be a single terminal, or there can be a single terminal followed by a single non-terminal. Okay, but here it is mentioned that terminals and non-terminals on the right hand side can be of any number. On the right hand side here we have three terminals. Okay, but it is saying that there should be only a single terminal, or there can be a single terminal and a single non-terminal at the maximum. At maximum it can have a single terminal or a single terminal and a non-terminal. But this one is saying that on the right hand side you can have any number of terminals or even any number of non-terminals. Even in the deterministic finite automata or any other automata, we have always done simplification. Simplification means if there is repetition of certain productions, okay, in a grammar, we can just remove it. If certain productions, we find them that they are not necessary, they are not important, we can remove them. So if a grammar has 10 productions and out of 10, there are suppose 3 to 4 productions which are meaningless. Okay, why we say meaningless? Because maybe if you remove those productions, the other productions are sufficient to just explain your grammar. Okay, if that is possible, for example, in case of finite automata, you remember certain states were removed to just simplify it. Similarly, Sometimes in grammars also there are unnecessary productions that you need to remove so that your grammar will become a simplified version of itself. Okay, so similarly, now we are going to cover CFG simplification. It means your context-free grammars simplification. Okay, so in a CFG, it may happen, it means in the context-free grammar, it may happen that all the production rules and symbols, which symbols? Non-terminals and terminals and production rules. Sometimes it happens that all of the production rules and all of the non-terminals and terminals are not required for the derivation of the strings. And there may also be some null productions and unit productions. Now I will explain you what these null productions and unit productions is while we will remove them. Okay, so elimination of these productions, which productions? Unimportant productions, symbols, is known as the simplification of your context-free grammar. So there are the following steps that we will do. The very first step is we will reduce the CFG. Reduce means unnecessary productions will be removed. What is the reduction? Reduction means unnecessary symbols and productions will be removed from the grammar. So reduction means focusing on these two. Next, after doing this, next will be removal of unit productions. Now I will tell you what are unit productions, how they look like, and after that I will tell you the removal of null productions. So after performing all these three steps, the grammar, the final grammar that will be generated, it will be called as simplified version of that grammar. So very first one is, you remember this very first one? That is reduction of CFG. First, we will do this reduction of CFG, reduction of context-free grammar. So it happens in how many phases? There are 2 steps to perform it. Okay. So first, we will focus on the first step. Okay. So first phase says that derivation of an equivalent grammar. If I have a grammar G, this is my context-free grammar, and I am simplifying this grammar. So the final simplified grammar that I will get G dash, I have to make sure that both these grammars are equivalent. Simplifying something doesn't mean that it has reduced, it has just, it has become meaningless. This is grammar G. I have reduced it and I have got a new grammar G dash, but this grammar is now meaningless. I don't mean this. I mean this, that when from a grammar G, I generate a simplified version of it, they should seem equal to each other. This grammar should be able to do all the work that your normal G grammar was doing. It means they should be equivalent. This should be reduced and equivalent version. It should be simplified and equivalent version. Okay, so if the G is the grammar, so its equivalent grammar is represented by G dash. Okay, so derivation of an equivalent grammar G dash from the context-free grammar G, okay, such that each variable derives from terminal string. Just focus on it and it will be more clear. So what is the derivation procedure? Include all symbols. First of all, you have to include all the symbols in W1. So there is one symbol. We are going to create one symbol W1 and I am going to include all the symbols. You know that in my final grammar that I am driving, there should be some symbols, terminal, non-terminals and all so on. So the very first, I am generating a W1. Okay. So all symbols, all the symbols that are present, I have to include them in W1 that drive some terminal. Which symbols I have to include in W1? Only those symbols I have to include in W1 which symbols are driving terminal symbols. It means suppose I have a production A that goes to A, I have a production B that goes to B, I have a production C that goes to small c. Okay, so these symbols, can you see? A is also driving a terminal symbol, B is also driving a terminal symbol, C is also driving a terminal symbol. So all the symbols, okay, I have to include them in W1 Why? Only if they satisfy the condition that those symbols are driving some terminal. So they satisfy. A is driving a terminal, B is driving a terminal, and C is also driving a terminal. So it means this W1 will have A, B, and C. They are candidate. They can enter in it because they are driving A, B, and C terminals. In step 2, include all symbols. In step 2, we have to include all symbols in I plus 1. It means in W2. Okay, that drive Wi. We have to consider all those symbols that are generating any one of this. For example, in the same, I have a production that says S goes to A, B. I have this production. Okay, or I have a production S goes to A, suppose. This is the production. Okay, so do you think that this symbol is driving a symbol A which is in W1? Yes. So in W2, I have to consider those symbols which are driving any symbol in it. So it means S is here. So we have to do this again and again, until and unless we are left with nothing. Phi, we are nothing, we are left with null. Let me explain you this phase 1 with an example here. So we have to find a reduced grammar equivalent to the grammar G. The grammar given to you is this, that there is a production P and this start symbol is generating AC and B, both. Start symbol is generating AC also and B. A is generating A, C is generating C, and BC also. E is generating this. Okay, so you remember the very first step says include all symbols that drive some terminal, only terminal. Okay, so here in this production, which symbols only generate a terminal? This S is generating non-terminals, so I will not consider it. This A is generating terminals, so it means I will consider it. It means this, see, can you see this is W1, right? So here this is only written that how many terminals we have. We have A, C, and E. Your process start from here, weight 1. Okay, so in weight 1, I have to consider all those symbols which are generating your terminals. So this was not generating terminals, so S is not there. A is generating a terminal, it is here. C is also generating a terminal, it is here. E is also generating a terminal, so it is here. So can you see your weight 1 is it has got these three symbols, A, C, and E. From using which rules? A goes to A, C goes to C, E goes to A. You can use either rule. E goes to A also says that there is a terminal, or you can use this also. So here they have used this rule. E goes to A. Okay, so there are three symbols we have here, right? After that, what W2 was saying? W2, it means next weight was saying that include those symbols which are generating W1. It means these symbols of W1, A, C, and E. These are the symbols of W1. Is there any production which is generating these symbols? If I look at the productions, so don't you think that this production S is generating AC also, and it is generating B also? And this AC and B, at least A and C, if I don't talk about B because B is not here. So this S is generating A and C at least, which are present in W1. So it means in W2, other than A and C, I have to consider S also. So I have written ACE from W1 union. I am considering one more S. I am just adding it. I am making it a part of it. And which rule I am using? I am using the rule S goes to AC. So now this W2 has become what? It has become A, C, E, and S. It means nothing is generating it. This phi says nothing is generating it. And your W2 is ACES. And W3 is also same, ACES. Now when two weights, they become same, they look same. Since W2 and W3, they have become the same, it means we have to stop here. Now we can drive our G dash. Our simplified grammar has which non-terminals? It has A, C, E and S as the non-terminals. Okay, and using these productions, the reason it has using these productions, it has the same rules, A, C and E, the same terminals. There is only one production, there is P production and there is a starting symbol, right? There are non-terminals, there are terminals, there is a production, there is a starting symbol. And what is the production? See which productions are present, which are removed. S2 AC is kept, S2 B is not kept because B is not in it. The non-terminals have no B, so only S2 AC was considered, A to A is considered, C to C is considered. This BC is removed because B is not present. E to AA and E is considered. So in phase 2, from where you start? You start, here we have W, here we have Y. The very first Y1 that you create, you keep starting symbol in that. So the phase 2 says that include the start symbol in Y1. Okay, include the start symbol in YI and initialize I to 1. It means this will become Y1 and it has the start symbol in it. Can you see? In Y1 we have the start symbol. After that we have to generate Y2. Y2 will have which symbols? Those symbols that can be derived from Y1. It means Y2 has those symbols which can be derived from S. What is there in Y1? S. It says include all symbols in Y2. Which symbols you have to include that can be derived from S? So if S is used to derive A, B, it means in Y2 you have to include A and B. So can you see here, from S which symbols can be derived? Now you have to focus on this production and not this production. Now my focus is here because I have reduced it to here. So from S, which symbols I can derive? I can derive A and C only. Okay, so in Y2 I have S from the previous and I have included that from S I can derive A and C, so I have included A and C in it. Which rule I have used? I have used from S you can derive A and C. After that, what you have to do, you have to just repeat this step again and again. Now you have three options, S, A and C. Now in Y3 you have to write which symbols can be generated from S, A and C together. So from S, A and C, if you see in the production, from S you can generate AC, that is already present. From A you can generate A, so A is here. From C you can generate C, so C is here, by using these two rules. Okay, so I am repeating. Let me just so how to start in phase 2? Very first thing is you have to consider Y1, and in Y1 you have to put the start symbol. Now my focus is on this production. Okay, I'm not considering this. Now in Y2 you have to put those symbols other than S, those symbols which you can derive from S. It means S will take you to which symbols? You can see that S is taking you to A and C. It means I have to consider A and C in it. This is my Y2. Next, in Y3, you have to consider those symbols that you can generate from these S, A and C. So if I look from S, I can generate A and C. That is already here. So I will not write it again. So I will directly write from S, I will get A and C. From S, I will get A and C. Okay, from A I can generate, can you see this? From A I can generate A, from C I can generate C. So these two are also a part of it. Again you have to generate Y4. From S where you can reach? From S you can reach A and C. From A, you can reach A. From C, you can reach C. It means this is a dead end. Y3 is equals to Y4. So now this is a point that you can generate a grammar. So what are the symbols? The final symbols left. Final symbols are S, A, and C. So if you put them in an order, it is A, C, and S. And in this, only two terminals are left. That is A and C. There is a production and there are set of rules. And what are the productions we are left with? We are left with S goes to AC, A goes to A, C goes to C. We have no E symbol left here. So it means E will also be removed now. So what is a unit production? So any production of the form like this, from one non-terminal you reach to other non-terminal. It is known as unit production. Okay. From M you reach N. From X you reach Y. So these are the unit productions. From one symbol you are reaching to the another symbol. Okay. So with that, I hope that I will explain it to you more clear in the next class. And with that, I am stopping this.